Hello and welcome to another slugging session. How about that? Didn't expect that? Didn't expect that yet again? Hello, hello. So today we are adjusting our layout, right? I forgot to adjust it before the stream. So today I decided to continue the series of mini Excel. So I didn't want to do that because I thought maybe I explored everything, but it went okay. So maybe we can continue and actually finally finish this entire project. You can find the source code of the project in here. If you're watching in like live, you can find it in the chat. And for people who are watching on YouTube, I'm going to put that in the description. So the source code. Right, and we started this entire thing on a previous episode of this series, so I'm gonna leave the link to the previous episode in the description as well. So it is not out yet, it's not published yet, so it's probably gonna be published after I finish today's stream. So the idea of the mini Excel is rather simple. So you have a CSV file, right? You have a CSV file, and in the CSV file you have cells that are similar to the Excel cells, right? So they can contain text, or they can contain numbers, or they can contain expressions, right? So the challenge is to write a batch program that takes this CSV file and actually evaluates all of the expressions in the cells and prints evaluated state, right? It also needs to keep track of dependencies between the cells, and it also needs to keep track of whether there is a circular dependencies and stuff like that. And there is a circular dependencies, it should report an error in some way. So we managed to implement it in to the point where it can actually handle this specific input, but it supports only, you know, plus operation and nothing else. To add support for other operations, you need to put a little bit of more elbow grease, and maybe that's exactly what we're gonna do today. So yeah, today I also wanted to clean up the source code a little bit, improve the memory management, because right now the memory management is actually kind of like very hackish. We just, you know, malloc things and never free them and stuff like that. It will be interesting to just like, you know, tidy up a little bit and just improve the quality of the source code overall. Right, so let me fetch the latest stuff. I think I already fetched the latest stuff, so as you can see I just checked everything in here, that everything works. So, and the input looks like this. Pakel1, thank you so much for Twitch Prime subscription. Thank you, really appreciate it. Your first subscription, by the way. So here's the input file, and we're gonna feed it into the mini cell, and as you can see it actually evaluated everything. So A indicates the column and number indicates the row, just like in Excel. So A1 is 1 and B1 is 2, so 1 plus 2 is gonna be 3. Right, as you can see, it's 3. So in case of A2, B2, we're summing up 3 and 4, and there you go, here is 7. So as you can see, we do all of the computations in floating point. That's why we have like this, you know, trailing zeros in the fraction and stuff like that. So it also handles the circular dependencies, right? So this one is A1, 2, 3. Right, so maybe we can put something like 3 in here, right? So now this thing depends on the value in this cell, and here I think this is B3, so this cell depends on this cell. So now we have cells that depend on each other, and if you try to evaluate this entire thing, it will tell you that circular dependency is detected. Interestingly enough, it actually prints and evaluates as it goes. You see, it managed to actually print the rest of the cells, but once it get to other things, it actually detected like circular dependency. I'm not sure if it's a good idea generally. Maybe we should first evaluate everything and only then try to print the final state. So we'll see about that. So yes. Alright, so let's start Emacs. I think I already have an Emacs started, so I'm gonna go to the mini cell in here, right? So, and let's take a look at a couple of to-dos. It's really strange. So here is the recent commits. I think I didn't merge the latest stuff. Yeah, I need to merge the latest stuff first. So, and then if I go in here, right, we have a couple of to-dos, right? We have a couple of to-dos in here, and on top of that, I think we have a couple of issues in the issue tracker, all arithmetic operations with the precedence and parentheses and stuff like that, and better error reporting, because as already mentioned right now, if you have a circular dependency, right, it will just tell you that there is a circular dependency, but it doesn't really tell you where, all right? So it's not particularly convenient. It would be nice to know where exactly the circular dependency has happened. Right, so that's one of the things we can implement in here. So the first thing I wanted to address is this thing. So right now we have expressions, right, which are essentially abstract syntax tree. Right, and the way we allocate memory for the abstract syntax tree is that every time you need to do a recursive reference to the expression itself, we just malloc some memory. So, and yeah, basically the entire thing is, you know, spread across the memory and it just forms a tree. And the question is, how are you supposed to deallocate such expression? Right, so I suppose you will have to write a recursive function that traverses like literally everything, and then as it unwinds, it would start deallocate the tree, right? So essentially, let me take a look. Let me take a look. Right, so imagine that you have a tree, right, and it has a bunch of nodes that point to other nodes and then point to other nodes and so on and so forth, and then you have a pointer to the root and stuff like that. So to deallocate this entire tree, you will have to recursively traverse the tree until you reach the leaves. And as you reach the leaves, only then you would start deallocating each individual node one by one, and so on and so forth until you deallocated the entire thing. Right, which is rather slow, I think, and very inefficient, because we know that all of these nodes have to be deallocated at once. Dipsy gifted tier 1 sub to whom? To Sinskit. Thank you so much for gifting tier 1 sub, and Sinskit, welcome to our epic tree traversal club. Right, thank you. So we have this tree, right, and to deallocate it, we have to traverse it, and then as you unwind from the recursion that traverses this entire thing, only then you deallocate. Interesting enough, if the tree is big enough, you may have a stack overflow, right, and also you deallocate or each individual node one by one, and interestingly enough, that each individual node is actually the same size object, right. You could have pre-allocated like a lot of such objects, like array of such objects, and then deallocated all of these objects at once. Right, so writing such deallocator, it's actually a lot of work from the programmer's perspective, because you need to write a recursive like traversal function, and also from the computer perspective, because you need to like traverse this entire thing when in reality you don't really have to. You have a bunch of objects of the same size, just pre-allocate them in a memory, and once you're done with them, just deallocate all of them. It's just as simple as that. It's just a chunk of memory. Allocate one chunk of memory, deallocate another chunk of memory. So and that's precisely what I wanted to fix with our program, because our program just, you know, forms this tree, and in fact right now it doesn't even deallocate it. But here's the thing. Okay, we can basically pre-allocate all of these nodes. We can take each individual node. So this is going to be node 1, 2, 3, 4, 5, right? So, and then instead of like deallocating them on a heap, I would allocate like a huge array, big enough array, not huge array, but big enough array. And each individual cell of that array is going to be that node in here. 2, 3, 4, 5. How many of them do we have? We have precisely 5 of them. And then within this entire thing, I would say that 1 refers to 2, then also 1 refers to 3. 3 doesn't refer to anything, 2 refers to 4, and it refers to 5, right? And every time I need a node for the expression, I will just take it from this array. But the question is, how big should be the array, right? How big should it be? It should be big enough so we can accommodate as many nodes as we want. So we can try to implement it as like a stretchy buffer, meaning that if you ran out of nodes in this array, we can just use reallocate, right? Realloc, right? This function. Realloc this function. But the problem is, every time you reallocate this array, all of the pointers, if you hold any pointers to the element of that array, they get invalidated, right? So essentially, if you store your nodes in this kind of array, and then you want to extend the array, all of the pointers here are going to be instantly incorrect because the entire array in the memory, in the RAM, got moved to a different place. So you can't use pointers to express a relationship between the nodes anymore. Right, if you want to have this like stretchy buffer that extends as you allocate more and more memory for your nodes, right? So you can't use absolute pointers. So the way people usually solve it is instead of describing relationships between the nodes with pointers, they describe them in terms of indices within that global pool of objects, right? So here we have an expression node. Here we go. So expression plus, and it points to the left-hand side expression and a right-hand side expression. So if we implement this sort of like a pre-allocated pool of expressions, right? Instead of having pointers, we can say that this is going to be an index in that global array of these things, right? And index is actually insensitive to reallocation, right? Basically, it's offset from the base of that array. It's simply an offset, and it doesn't care where that base is located whatsoever. And that enables actually a lot of pretty interesting tricks. Again, it enables you reallocating your array in whatever place you want in the memory. And on top of that, it actually enables you serializing your entire tree quite easily. So essentially, you can just take this entire array, dump it into the file system, and then on the next run of your application where all of the pointers and all of these segments are completely different, just load it up and it's still going to be valid, right? Because the pointers now are not absolute. They're relative to the base of this entire array. You see what I'm talking about? It's actually pretty cool. So, and this is like a common trick that, very cool people like Casey and John use in their games engines and stuff like that. And I've never actually tried to develop things like that. Well, I mean, I sort of tried it, but I never actually did anything serious with this kind of stuff. So I wanted to like take this as an opportunity to implement one of these like allocators and whatnot. Want array we will use because slow as F to traverse when you need to search for an element. It won't. So as virtual pointers rather than actual pointers. Yeah, sort of. Like, index is basically a pointer, right? Index is basically a pointer, but it's a relative pointer. It's relative to the beginning of the array. You can actually think about indices as pointers. Yeah. And furthermore, by the way, pointer is precisely 8 bytes on the 64-bit machine, right? It's 8 bytes on a 64-bit machine. What if you have a lot of different objects, right? And they all refer to each other. And you don't really, well, you have a lot of projects, but how to say that? So essentially what I'm trying to say is that you can control the size of the pointer now. Right, if you're using absolute pointers, you're stuck with 8 bytes per pointer. But if you're using the relative pointers, aka indices, you can actually control how much memory you can use per pointer. You see what I'm talking about? And if you build a data structure that you're going to serialize into the hard drive and you have a limited memory and stuff like that, it could be actually quite important. So, you see what I'm talking about? It's actually pretty cool. All right. So let's try to implement this entire thing, right? So let's just go ahead and try to implement it. Deep Singularity, hello, how are you? So yeah. So I hope my explanation actually made sense. Again, I'm not really super experienced with this kind of like relative pointer stuff, right, where you have a pre-allocated pool of objects and objects refer to each other but not through the pointers but rather through indices within that array. But I hope it was kind of like you know, managed to get the idea across. So maybe as we implement this entire thing, maybe it's going to be a little bit more clear what I mean. So yeah, let's go ahead and do that. So let me create a separate branch, and it's going to be a relative pointers, right? So this is going to be relative pointers, and we're going to remove this entire thing. So I suppose I want to actually create a special object, right, which holds the stretching array of expressions. So yeah, when we parse a primary expression, we always allocate, which is basically malloc an expression, and another malloc. Yeah, so as you can see, we do a lot of allocations of the objects of the same size, essentially. So yeah, here we allocate memory for, how is it called, for the file. So we're basically allocating memory for the content of the file. And then here we're allocating memory for the cells, but it's a completely different situation. So anyway, where is the expression definition? I think it's defined somewhere in here. There we go. So the thing I want to define now is something like expression buffer, right? So this is going to be expression buffer. And expression buffer is a stretchy buffer, and stretchy buffer usually have the amount of elements that they already have and the capacity, how much memory already allocated for the elements, right? And on top of that, we're gonna have a pointer to the beginning of the array. So it's gonna be something like items. There we go. What I want to do now, I want to create a function, right? So it takes exper buffer. And basically allocates a new expression in here. Right, and I suppose instead of returning a pointer to the expression, right, it's gonna straight up return you an index. And also maybe for the index, we wanna have a separate like type def size t expression index, right? Because it's going to be rather convenient for documentation purposes, right? So if a function accepts expression index, we know that it's something within an expression buffer, right? So expression index and expression buffer are sort of related to each other. Right, so it's not particularly type safe, but making this kind of stuff type safe is just like a lot of work that I don't want to put into right now. Okay, so we're not gonna accept any arguments in here, right? So there we go. Oh yeah, we need to accept the pointer to the expression buffer. Right, so this is the expression buffer. All right. So now we need to check if we have even enough memory for a new expression in this array. So if the amount of elements is greater or equal than capacity, right, what we'll have to do, I presume, we'll have to extend the capacity, right? The usual trick with this kind of stretchy buffer is that just multiply the capacity by 2, right? So the bigger the capacity, the faster it grows. And this is needed to ensure that you're not going to do too many reallocations, right? Because reallocations are quite expensive, so it's better to grow the size of the memory exponentially, so to minimize the amount of times you have to reallocate memory at all. Because the reallocation of the memory also does all sorts of things with the data structure of the heap, and also it needs to take the whole chunk of memory and copy it to a different place. All of that is very slow, so it's better like grow exponentially. All right, but initially the capacity is going to be equal to 0, so we need to check if the capacity is equal to 0, right? So we're going to assign it to some sort of like initial capacity, like 128 or something, whatever. It's like I chose this number completely arbitrarily. I didn't put really too much thought into this number. Right. So, well, the only thought I put into it is that it's just like a power of 2, because it's programming, right? Programming is all around, it's all about like powers of 2 and stuff like that. So after that, what we want to do, we want to reallocate the items, and we're going to use the new capacity in here, right? So, and then we're going to put this thing in here, right? There we go. So we reallocated everything. And after that, since we just need to return an index, we're gonna return the amount of elements. So basically the amount of elements already point at an index. Right, and of course, after we allocate it, we need to increment the counter, indicating that some of the item was taken, right? So that's basically what we're indicating in here, and we implemented a simple allocator for the expression, right? So I also want to have some sort of a function that accepts the expression buffer and the expression index, and turns it into an absolute pointer, right? Because even though these are relative pointers, you still need an absolute pointer to actually get an access to the specific element, right? And here within that function, I would like to perform the range check, right? So we need to double check that the index is in fact correct, and the correct index must be less than the count, right? If it's equal or greater than count, that means this is an incorrect index, and we want to report that to the user as soon as possible. Well, I mean, not really to the user, because asserts are not for the users, they're more for programmers, right? But we want to fail as soon as possible so the programmer can fix it as quickly as possible, right? So that's the point of range checks, right? So range checks are important. If you don't do range checks, your program becomes very unstable and susceptible to all sorts of vulnerabilities, and that's why Rust is a huge thing, because apparently it's a huge revelation of generating boundary checks into your program automatically. Anyway, so what we need to do in here is we need to take the items right by the index. Here with assert we checked that it is a correct index, and we're going to return this as a pointer, right? So there we go. We have two functions. The first function allocates the expression within that buffer. It stretches the buffer if it's needed, right? By the way, it stretches it incorrectly, because realloc accepts the amount of bytes, but here I put amount of elements, so I need to convert it into the amount of bytes. So yeah, I need to multiply it by the size of a single expression in here. All right, so let me try to compile this entire thing and see if I didn't make any mistakes. Right, first try. Did I even save everything? Right. Oh, okay, so I just implemented it the first try. It do be like that sometimes. Okay, so I think that's pretty much it. The way you create such structure is essentially you allocate this structure on the stack, right, and zero initialize it. And since I follow zero initialization rule, zero initialized expression buffer is a correct buffer. So essentially, because of the zero initialization, the capacity will become zero, and we do handle the zero situation. For the zero situation, we just set some sort of initial capacity, and then it will be reallocated automatically. So another interesting thing is that we primarily want to assert that maybe the items in this particular case will be null, right? If the capacity is equal to null, but items are not equal to null, it's kind of sus, not gonna lie, because yeah, right, it's basically it's inconsistent state. How is it compile so fast? You're compiling with Clang and Ninja? I'm compiling with Clang and no build. No build is my custom build system. You can find more information about this build system in here. And for people who's watching on YouTube, I'm gonna put that in the description. No build system, right? So it's a build system where you write build recipes in C itself. So this is how it looks like. This is the build recipe. So this is the script that builds this entire thing. It's written in C. All right. And also the program is very small, so that's why it's so fast. Anyways, so to use this entire thing, we just need to allocate it on the stack, right? And after we're done using it, we can just free the items of that thing. There we go. So that should be pretty much it. Let me see if this entire thing compiles. It seems to be compiling. Okay, so now we need to go and perform the compiler-assisted refactoring, right? So I'm going to change the definition of expr plus. So as you can see right now, it stores everything with absolute pointers. We need to convert them to relative ones and essentially indices. So it's going to be index, right? So, and that will break the program in all of the places where we use this entire thing, and we're going to follow the compilation errors. We're going to fix all of them, and this is how we're going to perform the refactoring, right? So we basically let the compiler to guide us through the process of the refactoring. You just change the definition, and everything breaks. You fix everything. You refactored everything. So this kind of technique actually allows you to refactor more sophisticated things than usually IDE, but it's at the same time it's a little bit more tedious, right? IDE is usually faster. This one is slower, but it's more precise, right? And you can do more things than with IDE if you use the compiler as the assistant for your refactoring. And it also doesn't work with dynamic languages, but I do not recommend using dynamic languages for serious software development. Anyways, so let's go through the compilation errors. Okay, so this one is interesting. So we have functions that parse everything and they return absolute pointers to the expressions. So we also need to change them, right? So a parse expression plus should also accept index, right? And I suppose to be able to allocate things within the expression buffer, we need to accept the pointer to the expression buffer. There we go. So now all of these functions will accept the expression buffer pointer. All right, so this one has to be LHS index, right? So this one is going to be index, and I suppose this function also should return the expression index and accept expression buffer. There we go. So in here, what do? We do that. So this one has to be also an index. Right, also accept UB. And look, we are allocating an expression in here. So now we have to allocate an expression the following way. So expression index, expression buffer, alloc. Was it alloc? I think I called it alloc, right? So yeah, I provide the expression buffer, and there you go. It gave us the index, right? But I still need to access the internals of the expression itself. So that's why I'm gonna do expression buffer at expression index, right? So I'm gonna return this expression index from the function, and I'm gonna use the absolute pointer to this expression to initialize everything, to at least memory set everything, then set the kind and left-hand side and right-hand side. And since left-hand side and right-hand side already indices, so that should just work. I think I should actually do something like index, right? And then here we're returning index if we don't have a right-hand side thingy. So I think I managed to refactor this entire stuff. And yeah, here, yeah, so this is a different function now. Here we are allocating expression yet again, so we have to do expression index, expression buffer alloc, right? And in here we're gonna just do expression buffer at expression index. There we go. And then we memory set everything, then we initialize everything. And then we'll have to return expression index. There we go. And here LHS, oh, this one has to be an index, of course. Thank you, compiler, very cool. All right, so this looks like a different function. So we have a function that dumps expression, which is very useful. Right, it just prints the AST of the expression. So in here, I suppose we need to accept the expression index, right, instead of the expression itself. And to be able to dereference this expression index, we need expression buffer, right? So expression buffer, EB, is probably going to be a pointer to this entire thing. So here we'll have to first dereference that expression, right? I mean, turn it into an absolute value. So it's going to be expression buffer at AB expression index, and the rest of the stuff is going to be done like that. And let me see if it's going to work now. So in here we have to put EB like that, and LHS and RHS are already indices, so I don't have to change anything in here. Okay, so when I'm parsing the plus expression, I have to provide the expression buffer. So I'm going to provide a pointer in here, and I'm going to pass it like this. There we go. Okay, so this one is interesting. So incompatible integer something something something. Oh yeah, because this thing have to return an index, of course. There we go. So all right, so now we're parsing the table. So as we parse the table, we probably also have to provide expression buffer right here. It's going to be 9, and there we go. Okay, oh, this one is interesting. So AST. So we have another place where we refer to the expression by an absolute pointer. So I suppose this is something that we'll have to refactor as well. So I think I'm gonna rename it to index, and maybe the entire field is also gonna be called index. Right, that way, usually you have a particular cell, right? You have a particular cell and you access it like this. You convert it to as expression, right? And the expression here has an index, and then you can do index. So that should look okay, right? So I always try to pick the names for the fields of the structures. So when you write this long, like, access to these structures, they sort of feel like English sentences. I don't know if it's a good idea or not, but I kind of like it. So I take cell, I interpret it as expression, and I take the index of that expression. So I interpret it as expression index. Right, so it's pretty convenient. So API design, am I right? All right. I knew that you're gonna like it in OTPL. So I mean, who said that only C++ can be used for DSLs? You can use C for DSLs, right? So it's pretty cool. All right, so cell as expression index, and there you go. And there you go. Okay, so here, when I evaluate the things, I'm trying to evaluate the expression. Okay, so this function accepts the index. We have to change it to the index like this. Expression buffer at, and because of that, we'll also have to accept expression buffer. So it's going to be EB expression index. Right, so here's expression index. We do our magic with expression index. So, and what I was complaining about, I'm not quite sure. Right, so evaluate expression. So that means I have to pass EB in here, and that should be fine, hopefully. So this one is an index, but I think table eval expression, yeah, it accepts everything correctly. All right, so I don't have to do anything. And I also have to provide the buffer. Use of undeclared, so that means I need to accept the buffer here as well. So I have to now pass the buffer like in as many places as I can. All right, so, and I think cell. So this is the new signature of this thing. Do we have anything else? Okay, so when I evaluate the cell, I have to provide the buffer, right? So here's the buffer. Parse table from the content. Oh, and this thing now accepts the buffer. There we go. And here's the last thing. I eval the cell and I have to provide the buffer. And I think I actually refactored everything. So yeah. Now we don't store the absolute pointers to the expressions in our data structure, right? We store only relative ones, and they are relative to the array inside of the expression buffer. Right, inside of the expression buffer, relative to this array. So let's see if I didn't break anything. So hopefully I didn't. And I didn't, everything works. That's actually kind of interesting, but yeah, now the pointers are completely relative, and deallocating everything should be pretty simple, right? So because you just do that. Yeah, and we also build with FSanitize memory and stuff like that. So if we do some nasty stuff and also forget to initialize something, the client will tell us. So yeah, I'm pretty confident in this thing. It would be kind of nice to do a val grind on this thing. I think the last time I did a val grind with Clank with FSanitize, I had a really bad time. So I wonder if they're compatible, by the way. I remember like some time ago I just tried FSanitizer and also val grind, and that killed my entire system for some reason. Does anyone know anything about that? So Clang FSanitize val grind. So is that dangerous? Memory checking in C, comparing sanitizers. Sanitizers and val grind to find memory. Well, I don't think we're gonna get any explanation on that. So I simply going to switch to maybe GCC and remove FSanitize memory. But maybe I'm gonna do it this way. I'm gonna just comment it out and just gonna create it like this. Gonna GCC. And we're gonna remove this entire thing. Okay, so now I'm gonna try to run this entire step. Okay, everything seems to be working even with GCC. And let's try to do val grind mini cell input to CSV. Hopefully it will work all right. 0 errors from 0 context. No leaks are possible. Right. So we keep track of a tree of expressions, and as we parse things around, we constantly allocate more and more and more expressions. And the cool thing is that now to deallocate the entire tree, we don't have to traverse anything. We just don't have to do that. What you have to do, we just need to allocate this single array, right? And as a matter of fact, here is the single call that allocates all of the expressions, the entire AST tree, like at once. That's the beauty of this entire thing. You just deallocate the whole thing at once, without traversal, without anything. And it's just like, yeah, it's easy. Super easy. It's pretty cool. So here we deallocate memory that we allocated for reading the files. Then here we deallocated the table cells. And here we deallocated the whole AST tree. So all of the memory is just completely gone, and just, yeah, only 3 frees. Slab style allocators, are they called slab style? Slab allocators. I know nothing about memory allocation, so yeah, slab allocators. Is memory management intended for efficient memory allocations of objects compared to early mechanisms that reduce fragmentations caused by allocations? The technique is used to retain allocating object that contains a data object in certain types for reuse upon subsequent allocations of objects at the same time. We don't really reuse anything right now, but I suppose it could be then modified to make objects reusable. It's not that difficult. So yeah, in any case, I'm gonna put that in the description for people who's watching on YouTube, just in case. Yeah, slab allocation. Slab allocation. What's the memory leak check you did? I use val grind. Val grind. It's a special profiler, I suppose. Yeah, it detects memory leaks and also profiles your program. So you can find it in here. Object pools, POG OOP, yeah. So well grind. Okay, that's pretty bold. Not gonna lie. And another thing that I heard is that this kind of stuff now makes it possible to serialize your entire AST tree. Right, I wanted to try that. Before I try that, I think I need to do a committee and maybe even push. All right. Okay. Implement an allocator for experts. Right, allocator for the experts. So let me see. So this is gonna be main. Let's actually rename main to 2 and create a separate main. There we go. So in here, all right, in here we're gonna have an expression buffer. It's gonna be 0 initialized, and then we're gonna free the items of this entire thing. Right, so we're gonna have a source code of some sort. So this is gonna be source 1 plus 2 plus A1 plus B2. All right, and we're gonna try to parse this entire thing. Parse expression. Right, so this is how you do that. We're parsing the expression. So the source code is going to be a pointer in here, and then we also provide the buffer, and that gives us the root of the expression, right? So expression index. So then I can try to dump expression, right? So you dump expression to a particular stream. You have to provide the buffer, and you have to provide the root, right? And 0 and level could be just 0. So that thing will just print the AST of this entire tree, right? And yeah, this entire thing has to be constructed like so. And I think I need to run this entire stuff. There we go. So here's our AST. Here's our AST. So the use of relative pointers is supposed to make it easy to just take this entire buffer and just dump it into the hard drive, right? Just dump it into the hard drive and then recover it. We could also maybe add more things in here, plus 69 plus 420, right? So yeah, here's the entire AST. So let's actually try to, you know, save the memory buffer. Why not? Expression buffer, I mean. So we have a lock. And now I can try to do something like expression buffer dump. Right, it will accept the file into which we want to dump it and the expression buffer itself, and we can pass it by a constant because I don't plan to modify it in this particular case. Right, so here we're gonna do a very simple thing. We're gonna first save the amount of elements in the buffer. Right, we're gonna save the amount of elements. We're gonna use the function called fwrite to do the binary write thing. So this is gonna be something like this. So I'm gonna do eb count. Here's the count. So the size is supposed to be the size of the single element. So this has to be a size of an expression, and the amount of elements is going to be wait, no, we're doing a completely different thing. So the size of the element has to be the size of the count. The amount of elements is going to be 1, and we're actually saving the you know, the count itself, right? And then here's the stream. So first we saved the amount of elements first. Yeah, so everything seems to be correct. And now we need to save the elements themselves. Right, so the elements are going to be items. Size of a single item is going to be this. The amount of elements, this one has to be actually this thing, right? The amount of elements is count, and we save it here. There we go. So that will basically save the entire state of the AST, right? You just take the whole thing and you just dump it, like as a binary dump. Right, so if I try to rerun it, everything seems to be okay. So now instead of dumping it into like a standard output, we're gonna open the file. So it's gonna be something like this: fopen expr bin, and we open it for writing in a binary mode, right? And then we close this entire thing, right? Expr buffer dump, and essentially I'm just the question is, we also need to save the root somehow, right? We need to save the root, otherwise we won't be able to recover the entire tree. So maybe as we dump this entire thing, we also need to accept the root, right? So it has to be something like expr index root. So, and in here we're gonna simply save the root. Right, so first one is going to be the count, then the root, and then the elements. But maybe count should be here, something like that. Yeah. So, all right. So looks good to me. So let's go in here. So we provide that. We provide the file, then the pointer to the buffer, and then the root itself. I actually want to call this thing the root. So it's going to be the root. And that should be it, right? So that should be pretty much it. So let's also print something. Saved the dump to S, dump file path, right? So this is going to be dump file path. Const char dump file path is going to be equal to this thing. There we go. There we go. Save the dump to expr.bin. Expr.bin. So if we take a look at the file system, now we have expr.bin, the size of which is 280 bytes. And if we take a look at this entire thing, maybe in hexel mode, we can see some stuff. Right, so here is basically the memory of the entire AST. Right, and as already mentioned, by the way, you can reduce the memory usage if you make the expr index smaller, right? So you know that you're gonna have like a few expressions, right? So maybe not more than 100. In that case, maybe you can just make the index something like uint 8, right? And for that, maybe we need to include stdint, right? So, and it saved the dump, and as you can see, it was 280, and if we refresh it, it's actually didn't save that much. it saved 8 bytes, 7 bytes. My mouse is dead. What the fuck? Excuse me. Oh shit, my mouse has died for some reason. I don't know why. Okay. Oh, I think it's my keyboard that died. Alright. So 8 bytes control the mouse, yeah. But if you have more bytes, like this amount sort of accumulates over time. You know what I'm talking about, right? And maybe you're gonna have several of such things per object, right? And because of that, it grows exponentially, essentially. But in our case, it just doesn't matter. It's just something that I wanted to, you know, check and evaluate if it actually changes anything. All right, so we dumped the entire AST, right? So we dumped the entire AST, and now let's actually try to load it up and see if it's still correct. Who knows? So I'm gonna remove the entire thing. So there we go. So everything about this source code, right? So the source code, by the way, the source code was this. I'm removing this source code, so we generated AST from this source code once, and we completely removed this source code. It does not exist anymore. That's it. It's gone. So the AST, so the only place where you can have this AST is this binary dump, right? And let's try to recover the source code from that binary dump, right? And since we're using relative pointers, it should be relatively easy, right? Should be relatively easy. Okay, so how are we gonna do that? I suppose I'm gonna just first open the file. So let's call it const char dump file path expr bin, right? So dump dumpy file path. We're gonna open it for reading in binary, and then after we're done, we're gonna close this entire thing. There we go. So, and I suppose I remember the first thing was the root, right? So we need to do expression index. This is the root, and we need to do fread. Okay, so I'm reading this entire thing into the pointer of the root. The size of a single element is the size of this thing, and the amount of elements is going to be 1, and we're reading it from f. So this is the first thing. Then we need to have a count, right? We need to have a count. So we're going to do fread count size of count 1f, and there we go, we read the entire count. Now we need to allocate enough memory for the expression buffer. So we need to do something like expression buffer ab 0. So I suppose I'm going to do it like this. I'm going to set the count to the count that we just read, and I also gonna set the capacity to the count. So interestingly enough, we could probably compress this entire thing, but maybe it's gonna make it less readable. And after that, I need to do items, and I need to just allocate enough memory for this entire capacity. There we go. So, and now we are ready to do fread, and we're gonna be reading the items. So the size of a single item is expression, and the amount of them is the count. We already know that, and we're reading them from f. There we go. So here we read the expression buffer from the file back. So we serialized it just by dumping everything into the file, and now we read it and deserialized it by just loading it into the memory. And now can we print the AST of this thing? Is it still a correct AST? Maybe it's not a good idea to actually do it like that, because I still need some of the variables in here. Specifically, I need the root. So dump expression, right? So if I remember correctly, this thing accepts this stuff, then we need to provide the pointer to this stuff, then we provide the root, and then we provide the initial level. Okay, so after that I'm gonna just return. There we go. So yeah, let's try to print this entire thing, and it still works. Here is the original source code that was lost, right? So, and the cool thing is that it makes it so easy to serialize the AST. Again, I didn't have to traverse anything, transform anything. Like all of the pointers that we use are relative pointers relative to the beginning of the array in which we store everything. So I can just dump this entire array into the file system and load it up from the file system. This is beautiful, actually. This is so cool. Like it simplifies managing the memory for the objects. It simplifies serialization, it simplifies deserialization. Why is this not talked more about? I don't understand. This is such a cool technique. It was just like, yeah, just use the indices in the arrays and just like, yeah. It's like a real life RAM. I guess, I mean, the arrays are stored in the RAM. So, yeah, it's pretty cool. And it simplifies everything. How the relative pointers differ, it's actually pretty easy. X per buffer, like this. So each relative pointer is an index, right? So you just look up that index in the array, and that's it. We also do, you know, the boundary check and stuff like that. And every time you need to work with it, you just dereference it into an absolute one, do whatever you want it to do, and forget about the absolute one. And when you pass pointers to the objects between the functions, you always pass them as indices, right? You only use absolute pointers for immediate modifications, and you forget about them as soon as possible, because again, the array in the memory can be reallocated at any time, right? So just quickly do what you needed to do and forget about it, because the next time it could be different. It's very trivial. It's actually a very simple technique. Jay, hello. What's up? What's up? What's up? It's actually pretty cool. I really like that. I only heard about people like developing things like that, but I never actually, you know, did it myself. It's actually pretty convenient, not gonna lie. All right. So even though we don't really need serialization, deserialization, I think generally it's actually kind of cool, just to be able to have that. All right. So input file. So here is one thing, and here is the dump. So let's remove all that test code. Is this populating by serialization is a solved problem? I don't know. I never heard people say that, but maybe they do. I know nothing about programming. I'm sorry. So I only learning all this stuff. Okay. All right. That's pretty pogue. Not gonna lie. So we have export dump buffer. Not sure if I want to commit this entire thing. Yeah, this thing is not particularly needed. And okay. Fix, what is it called? Fix, maybe I'm going to say typo. Right. So this is the typo. I'm going to push that right into the repo. Relative pointers. So should we make a pull request to our repo? We don't have a CI anyway. What's the point of making a pull request? You know, maybe we're going to set up the CI, you know, right away for the pull request. So maybe I'm gonna steal the CI from BM because I already have some CI in here. So do I need to have a formatting? I don't think I'm gonna include formatting for now. I don't think it's that important. The only thing I want to do in here is probably just bootstrap the entire thing and compile it and run it just to see if it, you know, compiles and runs. Haha. We don't need any third-party dependencies in here, so here we just bootstrap no build and we just do run. The run subcommand will build everything and then run the thing. So this is gonna be that, and this is gonna be that. All right, so this has to be a run. Build everything. So macOS doesn't require anything in here. So on Windows, this entire thing should also work on Windows. So we're gonna put it like this. All right, hopefully that will work. And let's go. All right. Set up ceremon was up. Hello. Let's push that. And let's make a pull request. Are we ready for a pull request? Probably. Kashey, what's up? Hello. Alrighty. And while we're waiting for some of the things already succeeded, which is nice. Oh shit, it's not gonna work on Windows because on we are using Clang and GCC. Yeah, that's a bummer. Right, so we have to distinguish between Windows, right? If we are on Windows, we have to use CLXZ or something like that. Yeah. You know what? I have an idea. Okay. There's no CI for Windows. Don't really want to deal with that right now. Disable CI for Windows. I'm gonna push that right into the repo. Oh, it's actually succeed. What the fuck? How did? Wait. How MSVC actually succeeded? I can't believe you've done this. This is not, well, of course everything is broken. Everything is freaking broken, but... Wait, what? You have GCC on Windows. Interesting. But, okay. But I still need to actually port some of these commands, right? So essentially on Windows, I'll have to like do this kind of thing, which is not particularly convenient, right? So yeah, I'll have to do something like define binary name, right? And by default is going to be something like mini cell, right? And if it's on Windows 32, it has to be exe, otherwise it has to be end if, right? There we go. And here I'll have to probably do something like concat, or maybe even join, maybe path between this thing and binary name. There we go. And then GDB, I'm not sure if you can have GDB on Linux. Maybe this kind of thing is actually completely redundant. It's better to just like use this thing directly. Right, and for instance on Windows you would do something like cmd cl.exe and just src main.c. And I forgot how you search for, how you specify the executable name. I think it's just VE, but yet again, bang, global, VE, So I suppose you do VE, mini cell, right, and it will be automatically with the exe, hopefully, right, so it's going to be else, and if, right, so else and if, and we don't need to do anything here, I suppose. So yeah, it feels like a lot of work right now that I don't really want to do, so I'm gonna just like really disable the Windows build, because again it needs testing, it needs that. I'm just not really motivated to do it right now, so sorry. So the Windows build is gonna stay disabled, as it technically should be in my opinion, but missing the oh yeah, I put a new line in here. I should not put a new line. Oh, okay. And this is where, by the way, not removing this file is beneficial, because the compilation of no build has failed. So now I can do move no build old back to no build, right? And just do no build yet again, and it rebuild itself properly. So saving no build old is actually very beneficial. And for those who doesn't know what I'm talking about, we recently implemented the self-rebuild system for our build system. So our build system is basically a C program, and it detects if it's modified and it rebuilds itself. You can watch me implementing this entire thing in, I think, on our YouTube channel. So I'm gonna put the video in the description. Sodding daily program that rebuilds itself. Yeah, so this is the video I'm talking about. So we did all of that on the stream, so we can find it in the chat, and for people on YouTube you can find that in the description. Program that rebuilds itself. There we go. The program that rebuilds itself. All right, that's pretty cool. That's pretty POG, if I say so myself. So, and maybe I also need to snitch up some of the to-dos. Snitch report repend body introduced in the pull request 3. Right, so this is the third pull request. There's no CI for Windows. We're gonna report that. To be fair, this is precisely what we were fixing, which is okay. Let's create an issue for this thing and instantly close it. Yeah. All right. So I think that's a cool idea. Now I have an issue to close for this specific pull request. Okay, so relative pointer for expression plus, so it's 5, and in here I'm gonna instantly close this. It's gonna be close 5. There we go. Farming commits, yeah, exactly. Just farm commits. Isn't that cool? I think it's pretty goddamn cool. My god. All right, let's merge the pull request. Cool, and also delete the branch. Issue farming. So the next one is gonna be relatively interesting. I think before we go into the next one, I want to make a small break and brew a cup of tea, right? So let me, where's my time stopwatch? Okay. Okay, let's take a look at some other issues. So did I fetch everything? I think I not really. I think I need to fetch the stuff that we just merged. And because I don't quite remember, so oh shit, okay, this is a classic situation. I created a bunch of to-dos, but I didn't really push them. Yeah, I forgot to push them. So I'll have to rebase it on top of the master super quick. There we go, so everything is rebased, and then maybe I can merge this thing and remove this thing, and let's actually push it into the master. Okay. So so what are the other to-dos? So this one is already closed. Maybe one of the things I'm gonna do, I'm gonna quickly purge some of the already closed to-dos. So this is gonna be purge. All right, something is broken. I don't know what exactly, but yeah. So maybe I'm gonna actually remove it manually. Something is broken within the Twitch. Remove to do 5. I'm going to investigate that a little bit later. The next to do. Oh, okay. So here we have functions. We have functions that accept string view, right? And they parse the double or int. So the reason why I don't use str2d or str2al directly is because they expect null-terminated strings, but string view is not null-terminated. So one thing first you have to do, you have to convert it to a null-terminated one, and the way to convert it to null-terminated one is allocate enough memory, put that string in there, and null-terminate it. So converting a null-terminated string into string view is easy, right, because you just take sub-views that doesn't contain null, and the other way around is more difficult and requires memory allocation. So that's why this is really, really inconvenient. So the way I did that is actually I allocated like a static buffer with fixed size. It's big enough size for my needs, but it's still you know, fixed one, and also it's a static one, and that makes it like really not thread safe. So it would be better to have something something that may be passable into the function, right? So some sort of like a very small memory allocator that you can pass into the function, and also stretchable, so you don't have to worry that your thing is not big enough. But for functions like str2d and str2l, it doesn't really matter that much, but just in case, you know, just to not worry that you don't have enough memory. So we can implement something. I don't know, we can implement some sort of a structure. I don't know. Temporary system. I don't know how to call it. We're going to call it temporary resistor, and this thing is going to have the pointer to the characters, right? Pointer to the characters, and the capacity of this entire thing, right? Right, the capacity of this entire thing. And I suppose the way it's going to work, right? So, temp resistor. Well, I mean, you're filling it up with data, so you have a temporary C string and you're filling it up with some sort of a data, right? So, and yeah, you accept this thing in here, so TC, we're gonna call it TC, right? And then we're gonna accept some sort of a data and the size of the data, right? Data size, right? And this interface will work with both other C strings or string views that have size. Right. So, and the way we're going to do that, right, first we can check that the capacity can hold the data size plus 1. right, if this thing is greater or equal than the capacity, what we'll have to do, we'll have to set the capacity to data size +1, right, data size +1, and then reallocate this entire thing, right? So we're gonna set the capacity like this. All right, so yeah, we're just stretching it up a little bit so it can fit there, and then we're gonna do memcopy tc sister, and what we're copying there, we're copying the data, and we're copying exactly data size amount of bytes. And since we know that data size +1 is going to fit in there, we're going to do tc sister data size is going to be equal to null terminator. So there we go, we have a null terminator, and then we just return the this thing from this function. Right, there we go. So, and the cool thing about this object is that it's you can keep reusing it, right? So it's gonna stay. The size of this thing is going to stay equal to the biggest size, right? So every time you try to fill something that is bigger than the string itself, is going to stretch it up a little bit. So, and that way you can reuse it between these calls. So, and hopefully that will reduce the amount of reallocations and stuff like that. Okay. So, and the thing we're gonna do now, I suppose these functions are gonna accept, and yeah, after you fill it up, you can completely forget about it, right? So you can just leave it as it is, and that's gonna be fine. So because of that, so here we can probably accept TMP sister, and it's going to be TC, and it's going to be pointed to this entire stuff. So here's what we do in here, right? So I suppose I'm going to do PTR TMP sister field. I provide TC SV data SV count, not const but count. Right, and then I put the pointer in here, right? I put the pointer in here, then end pointer, and there we go. I don't think I need to do anything else in here, right? So, yeah. And then I can reuse the same thing like between the calls to these functions, right? Because it always zero initializes everything, so it should be fine, I think. I think it should be fine. All right, so in here, we don't need to do that, so this one is going to be char ptr tmp sister fill. So it's going to be tc sv data sv count. Right, there we go. And I guess that is it. So I think now we can just perform the compiler assisted refactoring and go through the compilation errors and whatnot. Alright, so if it's not equal to PTR, the next error is, this one has to accept TMP sister, so it's going to be TC, and let's go here, PTR, did I do everything correctly? Okay. Alright, so here, when we parse everything, right, we'll probably need to accept TMP sister here as well, so it's going to be TC. Right, so then I can do this thing and I can pass this thing like that. So, and here I'll also need to, where is it? I need to pass the TC here as well. And when I parse plus, we can pass it as well here, like it would be better to pass it like everywhere. So, and the reason why I want to pass everything to the functions rather than having global variables is that because maybe later it's going to make it easier to parallelize this entire thing. It will be interesting to explore how to parallelize the computations for this mini XL. Probably first we'll have to determine what cells can be computed independently from each other, if you know what I'm talking about. right? So essentially, instead of evaluating cell, we can grab the cell and try to traverse its graph of dependencies and mark what cells we, traversed. Right, and then determine the independent clusters of the cells. Right, we determine independent clusters of the cells, and each individual independent cluster can be computed in separate threads. Sounds interesting? I think it sounds pretty interesting. Or better yet, actually, I don't know, maybe you can basically allocate a thread per cell, right? A thread per cell, and if the cell needs a value from a different cell, right, and the cell is in the middle of computation, that cell sort of locks and waits until that thing is ready or something like that. It could be something like this, and then maybe to not allocate too many threads, you would have a thread pool or something. It will be interesting. So yeah, exploring how to make this entire thing multi-threaded would be an interesting topic. I'm not sure if we're gonna do that, but yeah, sounds interesting nonetheless, in my opinion. Alright, so in here we're gonna pass TC, so a plus expression, have to pass TC as well, TC, TMP sister, TC, and here, TMP sister TC, alright. TC for sure here too. TC here, right? And so, and this is where we probably have to allocate it. So TMP sister TC. You can also zero initialize this entire thing, and there we go. All right, that's pretty cool. And then at the end of this entire thing, we can just deallocate TC sister. There we go. So yeah, this is the entire memory. So three things, three buffers, right? Three buffers. The buffer that holds the file, the buffer that holds the table cells, the buffer that holds the expression nodes for the expression AST, and the buffer that holds the temporary C string for like in intermediate conversions and stuff like that. And that's it. So this is the whole memory management. Right? We know that we have four regions of memories, and yeah, we're just treating them differently depending on what we need in them. Yeah, the entire program uses 4 regions of memory on the heap. I really like that. I really like that. I don't know why, but it just gives me satisfaction. So if I try to run this entire thing, and it still works. Okay, so we introduced another like sort of memory allocator, and everything seems to be working. Everything seems to be working. So, and on top of that, we can try to maybe run all of that with the memory sanitization of our nation. Oh, with Clang and shit, you know? All right, that looks cool. So if I build it with GCC, well, correct. Mini cell input CSV, and all right. 0 errors, 0 contexts, no leaks are possible. Okay, so that's pretty cool. That is pretty pogue, not gonna lie. So no memory leaks and shit. So what do we have in here? So this is basically the simple thingy that we introduced in here. So stretchy. So remember that I had a number, the issue number. So it's gonna be 6, right? So this is the 6. Implement, maybe introduce TMP sister buffer. Right, I'm gonna push that buffer right into the repo. Right into the repo. Okay, so did I push it? I think I pushed it correctly. Alright, so let's create a pull request. Let's create a pull request. So this one should close the 6. I suppose, if I understand correctly. Is it 6? Yeah, stretch a TMP buffer. All right. So wasn't that hard to implement? What's going to be the next thing? What's going to be the next issue that we can try to implement? Arithmetic operations, error don't. This one is interesting. Syntax for copying expressions from neighbor cells. You know what it means? You know what it means? Right, so in the Excel, in the original Excel, usually you can sort of define a formula, right? Okay, so holy shit, we have to wait until this shit blows up, of course. Can we actually make it bigger? Oh, I can. That's nice. So if I have something like this, right? So, and my formula is essentially this thing plus 1, right? And then if I sort of copy it, right? It's the formula gets copied, but also the cell gets updated relatively, right? So it gets updated relatively. I wanted to have a similar syntax for our mini cell. You know what I'm talking about? You know what I'm talking about? I think it would be kind of cool. So the way we can do that, so copy CSV, right? So imagine that we have something like A and B, right? And in A, we're gonna have like 1, right? So here is the value 1, and then the formula is going to be A1, right? So this is A1, so 0, 1, plus 1, cool. And then on the next one, I'm gonna say, so this cell is going to be a copy of this cell. Something like this, right? It's gonna be a copy of this cell, and what it will do, it will take this formula and update each and individual cell relatively, right? So basically, this will turn into the following formula. Right, it will turn into A2 formula, and so on and so forth. And that way, right, I can actually create a bunch of these things, right? And the results should be 1, 2, 3, 4, 5, and so on and so forth. It's sort of like a determine the direction, like cell from which cell you copy your stuff. So, and in here we can say that this is going to be equal to A1 plus 1. And right, so it's A1 plus 1, and again this entire thing is going to be just copy from this stuff. And what this thing will do, it will essentially yeah, it will update everything relatively. Yeah, so that's going to be the idea. And for different neighbors, maybe you can say I want to copy the expression from the left one, right, or from the right one. And the bottom one probably should be something like V, but it's a character at the same time, so it's kind of weird. Yeah, so it's kind of interesting. Not actually copying, but describing the action of expansion. Whatever, you can call it whatever you want. Okay. So, all right, is our pull request ready? I think it is ready. Okay, so this is going to be this. And the question is, how are we gonna do that? Are we gonna do that on the level of a parser or on the level of the evaluator? That's the most interesting thing. Is it gonna be evaluator thing or a parser thing? I think it would be easier to do that on the level of evaluator. All right. Yeah. Alrighty. Let's merge the pull request. That's pretty powerful, isn't it? I think it's pretty powerful. Oh boy. So let's go to the master. Let's remove this entire thing. I think I'm gonna make another small break. Yeah, I need to grab some water. So yeah. So let's make breaks between the issues. Next break. All right, let's quickly implement that. So this is the copy. So we need to implement this specific feature. I was thinking how we're going to implement this entire stuff, and I think I'm going to introduce a new kind of a cell. All right, so we have expression kind. I think it has to be cell kind, right? So we have a text, number, expression, and it's going to be called kind clone, right? So it's going to be called kind clone. And you also need to have like a thing that describes the clone direction, right? So it's going to be clone direction. Not necessarily maybe clone direction, but it could be just direction in general, right? So direction left, right? Then you have direction right, up and down. So you have different kinds of directions. Now, when you have a clone, so you have as, right, so you can interpret your cell as text, number, expression, or here you can have something like clone. And clone is essentially going to be the direction of the cell which you have to clone, if that makes any sense, right? So that's basically what we need to do in here. All right, so let's try to recompile, and hopefully that will throw a couple of errors, right? So now we know what to do. So here we're evaluating the expression, right? So we found a cell. So if our expression is a cell, right, and the cell is a number, we just return this entire thing. So interestingly, it feels a little bit redundant. It does in fact feel a bit redundant. So you evaluate the cell, but you don't get an expression of that cell. So if it's a number, you do that. If it's expression, you try to evaluate it. So, but if it's evaluated, you're gonna be doing it like that. What I'm thinking is, what if we always try to evaluate this cell? We're gonna always try to evaluate this cell. And essentially, after we evaluated it, right, we know that it's evaluated. So we don't need to do it in here. So text is never evaluated. The only thing that is evaluated is the cell kind expression. Right, and if the cell kind in here, right, the cell kind in here turned out to be cell kind clone, you will have to replace that cell with a completely different kind. Right, so that's one of the things we'll have to do. Unimplemented. Meaning that after the cell evaluation, a cell never should be a clone. It should never be a clone. Meaning that here, cell kind clone has to be unreachable. Right, it has to be unreachable. Assert 0 unreachable. There we go. So this thing is in fact unreachable. Okay, that's pretty cool. So essentially, if you have a clone, it will immediately clone the cell it points to, right? And it's not clone anymore. If that makes any sense, right? It's not clone anymore. Yeah. I think that's pretty cool. All right, let's try to run this entire thing and see if we have any mistakes in here. Okay, so now we are evaluating this entire stuff, and since we're evaluating this entire thing, right, it never should be clone, right? So maybe that's precisely what we're gonna do in here. Break is gonna be assert unreachable. Maybe we can even explain what exactly is going on in here. So cell should never be a clone after the evaluation, right? So unreachable. There we go. So that's pretty important in my opinion. That is in fact pretty important. So in here maybe we don't need these kind of things because exit automatically just exits everything, so return also automatically exits, so there's no fall through. I didn't see any fall through situation in here, that's for sure. So this is going to be some sort of one, but maybe not. Right. Looks cool to me. All right, so we have everything in here. All right. Okay, and I didn't break things. I think at least, yeah, so everything seems to be okie dokie karaoke. Yep. And now let's try to compute copy. So here's the copy, and in here, as you can see, we're trying to use the clone feature. Let's see if it's gonna work or not. So I think it's gonna work because we don't even produce clones on the level of the parsing, so we need to introduce some sort of a parsing. Right, so it's gonna be no bold, no... God damn it, I should stop reading the chat because, yeah, chat starts to affect me. It's kind of funny how like you glance at the chat and while talking and you start saying the words that you see in the chat. It's kind of funny. No bold. No bold. Oh, we're actually a pretty cool name for the build system. No bold. All right. So let me see. Copy CSV. All right. So, yeah, if I try to run mini cell, right, mini cell and copy, yeah, there we go. So they never even calculated because we do not even parse them as the direction or anything like that. Interestingly, one of the directions should be V, right? But what if you want to have a text that is just single V? So that's kind of strange, not gonna lie. So maybe we should, we could probably use like equals for this entire stuff, but equals already reserved for the formulas, right? Equals already reserved for the formulas. I don't know, maybe for the clone, we're gonna have a slightly different syntax and it's gonna be something like this. Right, so it's gonna be something like this. Right, so essentially equals is the formula, colon is clone, and after, it looks like a face by the way, it's like eyes and nose, right, and then you can just have something like this, there we go. Isn't that cute? Isn't that cute? I think it's pretty cute. I think it is in fact pretty cute. Okay, yeah, so I think that's pretty convenient way of doing that. So we need to go to the parser, parse table from content, and this is what we're doing here. Oh, there we go. So first we see that thing starts with equals, right, and that means we're gonna try to parse it as the equation. Otherwise, if it starts with colon, right, this entire thing starts with colon, we're gonna parse it as the clone, right? So sv chop left, we're gonna remove this entire thing from here, right? So then we set the kind of the cell kind clone, there we go, and cell, yeah, we'll have to actually switch between different things, right? So we need to have if cell value now is equal, SV equal to, let's say, left. This entire thing should be equal to left. So it's going to be cell as clone, and direction is going to be direction left. So that's basically what we have in here. If SV equal cell value right, this thing has to be right. If this thing is up, this thing has to be up, right? And if this thing is down, this thing should be down. So, and otherwise, we need to throw some sort of an error, right? fprintf std error, svfmt is not a correct direction to clone a cell from, right? So, and we're going to provide the direction here. So this is cell value. There we go. Here's a cell value, and we just exit this entire thing. There we go. So now we are parsing the cell clones correctly, hopefully. We'll see, we'll see. The winner gets T, that's for sure. We'll probably need to recompile this entire shit first. No build, and of course it doesn't even compile because we need to wrap those things in SV, because these are string literals, they are not string views. First you need to convert a string literal into a string view, otherwise you're not gonna even compile. And if you can't compile, you can't work, because if it compiles, it works. If it doesn't, it doesn't work. Okay, that's cool. It failed with assertion in a place saying unimplemented. That means we are on the right track. So it tried to hit the code that is not implemented yet. So, and that's basically what we're gonna try to do in here, right? So cell as clone, right? And this thing basically defines the direction. Oh, and to know the essentially the neighbor cell, I need to know my own coordinates, but I don't know my own coordinates because I passed the cell by a freaking pointer. Yikes. So what I need to pass the cell as, I need to pass it as a coordinates, right? Row and column, and then I'll have to do something like table cell at row and column and convert it to a cell like this, which is actually really familiar. Doesn't this look familiar? We have a similar shit for expression buffer, right? At, where you take an index and a buffer and it sort of dereference it into the absolute value. So essentially, table is the buffer, right? But the pointer to the element in that buffer is actually two-dimensional. So table is like expression buffer, but two-dimensional. Think about it. Cell index. Well, cell index is kind of incoming, but we already have something similar. Cell expression. Maybe expression cell. Yeah, expression cell, which is already row and column, and we use it for polymorphism between expressions, right? Because a single expression could be either a number, a cell, or a plus, and that's basically what it is. I think I want to make it a little bit more reusable, so I guess calling it a cell index is a good idea. Let's actually call it a cell index. Why not? Right, so, and in the table cell at, I can actually accept maybe a cell index, right? Maybe I can accept a cell index. Right. And in here is going to be index row column. Then in here I can do index row and index column. And I think this is enough for compiler assisted refactoring. I think it will generate enough errors for me to work with. So this one is going to be cell index. So yeah, now an expression can be number, cell index, or expression plus, which is a binary operation plus between the expressions. All right, in here, when I do cell at, I do row column. So maybe I need a way to construct a cell index from appears, but maybe not. I can actually do something like cell index, index, cell index, row, and this one is going to be column. There we go. And then I can just do cell index. There we go. So another one. Oh right. Oh shit. That makes it super fucking convenient. I think we're on the right track. Like, I mean, when the code starts to simplify and things just fall into places, yeah. Snakes, what's up? What's up? How are you doing? Really glad to see you. Okay, and in here we can actually accept the index. So this one is going to be cell index. Right, and then I can just do something like cell index like this, and then here's the cell, right? It's kind of similar. Apparently table is basically export buffer but for the cells and two-dimensional. This is so cool. And now, yeah, this is where I can do clone. Now I can have a function that accepts cell index and direction, right? Direction, and returns a new cell index, basically moves it in that specific direction. Represents an old arena libraries while trying to understand code here. All right, good luck. It actually sounds pretty interesting. I like exploring old code of, you know, legacy projects and stuff like that. It always feels like some sort of an adventure, right? You go on an adventure, you don't know what you're gonna expect, right? So you prepare, like you investigate, then you go like step through the debugger and discover some interesting things and stuff like that. It's not always pleasant, but it's always interesting nonetheless, right? And I also like reading someone else's code, by the way, because it sort of like reveals how the author's brain work. It's always interesting to actually like read someone else's code. I don't know, maybe I am weird like that, because I heard that a lot of people don't like to read someone else's code, but I do kind of like it. Like you see some old stuff and you had no idea that back in 2018 you didn't have some modern stuff. Yeah, exactly. Especially when it comes to C++. C++ from 2003 is completely different than modern one. Alright, so now we can have something like this, but we're not going to introduce it right now until we actually finish the refactoring. Alright, so conflicting types, so this one I suppose have to accept the cell index, so this is a cell index. So here is the cell. Oh shit, and the only reason, by the way, why I dereference it like that is because so I can evaluate it. But now the evaluator just accepts the index for me, so I don't have to do that shit anymore. But I still need the you know, the reference to the function, because then I'll have to, you know, print something in here. So I suppose I'll have to do something like cell table table cell at, and this is going to be the thing that, well, oh no, I'm actually evaluating everything. Well, yeah, so first I need to evaluate it, then I need to dereference it, and then only try to see what's inside of this thing. Okay, so that makes sense, I suppose. Yeah, you have to provide the table, of course. Anything else? Anything else? Table, of course. Of course. Of course. And here we have a row. Cell index, cell index. So we construct a row. What am I doing actually here? That's really strange code, but okay. Row. Wait, did I stash something? Okay, so I have a deja vu. I thought I already did that. But okay. So then here I can do evaluate cell index, and then I can grab the evaluated thingy, right? And then here I can do all of my dirty stuff. looks gooder to me, and there we go. So I think, yeah, cool. Now here we are accepting cell not by an absolute pointer, but by a relative one, right? And here we actually, you know, dereference it into an absolute one. But again, what I want to have a function that moves the cell index, neighbor cell, right? Maybe I'm gonna call it nbor because a neighbor is actually too much to type. So in here we're gonna accept cell index, right? So here's a cell index and the direction, right? Cool. And let's switch between different directions. So dir left, so I'm gonna copy paste this entire thing, go back in here, and in here we're gonna query replace comma with this thing, and now I'm gonna do something like that. So it's gonna be case cool. So what we're gonna do in here, if we need to go to the left, right? So left is basically decrementing the column. So we're gonna do column -1. There we go. Column -1. If you need to go to the right, it's column +1. Index column +1. Break. If you need to go up, it's a row -1. Index row -1. Break. If you need to go down, it's +1. Right, and then we just return the index that we modified. And if it's something that we didn't expect, this is straight up unreachable. Your memory is probably corrupted somewhere. Just like the Russian government or whatever. All right. So, and exit is gonna be please send help. Please. All right. Now we have a neighbor cell. Interestingly, if so, cell index, right? Cell index is size t. So you have to be super careful if you try to, I don't know, if column, for instance, right? If index column is equal to 0, this is straight up trying to access like a invalid cell. So maybe we want to report this as an error somehow. I don't know. One of the things we can try is essentially maybe pass the index by a pointer, and that will automatically modify the index, right? So we're going to replace index dot with index this, there we go. And in here it will return a boolean indicating that it managed to do something, I don't know. Right, so this is one thing we can do. But another thing we can do is allow negative values. I think I'm gonna allow negative values in here. And when I do table cell at, I'm gonna be checking not only that it's less than rows, but also greater than 0, right? Greater or equal than 0. I think that's gonna be beneficial as well. Right, especially when we do something like this. I don't know. So I'm just trying to think like how can we report that as an error, like a little bit nicer, but I don't think it's that easy. So so if it underflows, it becomes super big and it won't be a valid index anyway, so you're gonna fail with an assertion, but there will be no nice error message for the user. But I don't know, it's like a lot of different trade-offs. I don't know, we'll see. Whatever. Okay, cool. So here we want to have a neighbor cell, so it's going to be neighbor cell. I provide cell index and I provide the direction, so it's going to be cell as cell as clone. Right, there we go. So this gives me a neighbor index. There we go. I have a neighbor index, and then I'm gonna get a neighbor cell. Table cell at table neighbor index. There we go. Cool. And the first thing I want to do with this stuff is evaluate it. Well, I mean, I can just do something like table eval cell, table eb neighbor index, right? So if I need to get a particular neighbor, right, I first want to make sure that it's evaluated and it's not clone, right? Because you can clone clones. You see what I'm talking about? You can clone clones. So that means, oh, this one is actually going to be very interesting. So what if you, oh shit, okay. What if you have something like this? Do we even check for this kind of shit? I don't even know. I think we do. Yeah. So basically, we first when we are evaluating everything. So it's expression status. So we keep track of the evaluation status only for expressions, but not for the clones. That's what's interesting. So we don't keep track of evaluation status for the clones. So there's two options I see. We can add evaluation status to the clones, right? We just add it to the clones. And or we move evaluation status outside of the expression, so now cell has an evaluation status. Right. That is very interesting. So maybe the cell itself should have an evaluation status. And cells like basic atomic cells like text, number, when they are unevaluated, they evaluate to themselves. And that should help to keep track of this kind of stuff, I suppose. We can give it a try. So let's quickly actually go back and mark this as an implemented, right? And do a little bit of a compiler assisted refactoring, right? So basically moving the status from expression to the whole cell. So now the entire cell will have the status of evaluated, not evaluated, regardless of whether it's expression or not, right? So I think that would make sense. I think that will make sense. Okay. Okay, so I'm just like checking everything just to make sure that everything's okay. Okay, so expression cell, maybe there's the cell, and inside of the expression we have the status, right? So, and I want to move the status somewhere here. So the expression itself, right, it has value, has a value, and this one has a status. Maybe before I go, I need to commit whatever I have already, because yeah, it could become a mess. So let's do a committee first. I think that's gonna be very important. Committee, and then push. So we introduced the kind of a cell that is a clone, right? So which clones everything, and we also introduced the cell index. Okay. So where is the clone? Bitstream, what's up? Clone. I forgot the number of the issue. For copying expressions, okay. 7. Introduce cell index and clone kind kind of cell. Clone kind of cell, and we're gonna push that right into the repo. Alrighty, so this one is actually getting very, very interesting. Cell dot, right. Status is a part of the cell and not part of the expression anymore, hopefully. Okay, so let's go through this entire step. Okay, so the only place where it is important is this thing. So I suppose that we need to turn it into a switch, right? So this is going to be switch cell kind, right? Then we're going to have different cases like cell kind. Where's the cell kind definition? Cell kind. I'm going to move it in here, and we're going to put it like that. So it's going to be case. And I'm going to query replace like this. There we go. So, and yeah. Interestingly, for the text, right, you always set the status to evaluated, right? Status always evaluated. And the same for the number, right? So whether it's a text or a number, it's always evaluated. When it comes to expression, right? When it comes to expression, essentially, if you found an expression that is in progress, this is a circular dependency, straight up. Then if your expression is not evaluated yet, right? So, but that will require changing this stuff a little bit. I think I need to do it like that. So status. If it's not evaluated yet, we set the status in progress, then we evaluate specific expression, and then we set it to evaluated. Similar thing has to be done with the clone, right? If you try to evaluate the clone, right, but the clone itself, oh, by the way, this one has to be also status. The clone itself is in progress. You found a circular dependency. There we go. So yeah, like basically, it's rather interesting. So I already have on my paint, right? So you have three statuses, right? The first status is unevaluated. It's not evaluated yet. In progress, right? This is in progress, and evaluated, right? And essentially, you have a table of cells that sort of depend on each other, right? So essentially, you have this cell that depends on this cell, that depends on this cell, and depends on this cell, right? So, and in here, first, how you evaluate things. Okay, you start evaluating from here, right? And you mark this thing as in progress, right? Then you evaluate this thing and you mark this thing as in progress, and so on and so forth until you reach something that is evaluated, and you mark it as done, and then you mark this as done, right? Then mark this as done and this as done, and everything is essentially done, right? But if you have something that depends like circularly, right? Something that depends circularly, this is not going to work because you mark this as in progress, and then you try to evaluate this, and you mark this as in progress, and you try to evaluate this, and you found that it is in progress, and this is how you found the dependency. You see? That's how we find them, right? We have three statuses, and if you reach something that is also in progress while being in progress, there you go, you found the circular dependency. So yeah, that's basically what we're doing here, and that's how it looks like in the code, right? So you're trying to evaluate the expression, it's in progress, there you go. If it's an unevaluated, we mark ourselves as in progress, evaluating it, and then mark as evaluated. Similar with the clone. Similar with the clone. By the way, I developed this technique when I was developing Bosom, right? Because again, Bosom has dependencies, like bindings that depend on each other. And basically this is where I introduced this notion of the status, right? And it's actually very, very cool, I think. All right. So, right, if cell status unevaluated, right, if cell status, oh, this one is interesting, right. If this is a clone, it must be unevaluated. It just must be unevaluated, because if it's an evaluated clone, it should not be clone anymore, because the thing I plan to do is when you evaluate the clone, it basically clones the neighbor cell and it ceases to become a clone anymore. It becomes that cell, right? So that means this thing is unreachable. So if you have a clone that is not in progress and not evaluated, which is evaluated, this is incorrect, right? So unreachable. Evaluated clones are an absurd. When a clone cell is evaluated, it becomes its neighbor kind. You see what I'm talking about, right? So essentially, if you have a cell that is a number and you clone the left cell, this thing becomes that cell. It's not a clone anymore, so there should be no evaluated clones, right? So it's an absurd, and this is why it is an assertion. So this basically is unreachable, essentially. Does that make sense? Hopefully that makes sense. So just in case, I'm gonna put like one in here, but I'm not sure. All right, so unevaluated. So suppose I want to mark my cell now as in progress, right? So there we go. It is currently evaluating. Now I need to have a neighbor index, cell index, neighbor index, neighbor. So I don't think I want to call it neighbor cell. Neighbor, I think I'm going to call it indir, right? Neighbor in that specific direction. Neighbor in dir, we provide the cell index, and then we provide the direction. So direction has to be basically cell as clone, and clone is the direction. Okay. So after that, we want to try to evaluate that neighbor cell, right? We're trying to evaluate that neighbor cell. Provide the table, provide the expression buffer, provide the neighbor index, and there we go. So we made sure that the neighbor is evaluated. So the next thing we're gonna do, we're gonna set the kind of our cell to the kind of our neighbor. So we'll probably have to do something like cell neighbor table cell at and neighbor index. There we go. So this is what we're doing here. Right. So, and here's what we're doing. We're already cloning. So the kind of the cell becomes the kind of the neighbor, right? Becomes the kind of the neighbor. And ooh, this one is actually juicy, I think. It becomes the kind of the neighbor. And depending on the kind of the neighbor, you'll have to do different things actually. So we'll have to switch between different kinds in here. This one is interesting. Okay, switch neighbor kind, right? And what sort of kinds do we have in here? What sort of kinds? Cell kind. So we have text, clone. All right. So because if the expression is if the neighbor is an expression, we'd have to adapt it according to the direction. If you know what I'm talking about, we'll have to adapt it according to the direction. All right, so let me see. So it's gonna be, could replace this like this. Got this with that. So, and I'm gonna put it like this, so it's gonna be the case. All right, so cell as text. If we know that this is a text, we're gonna take the neighbors thingy, neighbors text. But maybe I could do something like, could I just do cell as neighbor as, cell as neighbor as? I think we could. And interestingly enough, if cell kind is an expression, right? If cell kind is an expression, cell kind, we'll have to do additional evaluation. So we know that we are not evaluated, and that means we'll have to do something like this. So we'll have to evaluate that shit, right? And only then we'll be able to declare this entire thing finally evaluated. Okay, so cool. If you have a clone, it's an evaluated, I mark it as in progress, right? Then I take the neighbor cell, I make sure that that cell is evaluated, then I clone that cell, right? And then if the cell that I cloned is an expression, I evaluate it, and then I mark myself as evaluated. But that's not it. That is not it. Because when you clone an expression, you have to adapt all of the cell references, right? You see, this cell references points to here. That means that in this clone, this thing should point at this entire thing, right? That means every time you clone an expression, you have to shift expression in a particular direction, right? So, and what's interesting is that the direction of the neighbor is up. Transform AST, exactly. God, somebody's paying attention. Oh my God. I looked at the chat and somebody's paying attention to what I'm doing. It's so nice. Thank you so much, Memtopil. All right, so yeah, essentially, look. The neighbor direction is up, but the direction in which we'll have to transform cell ID is down, right? So what we can do, we can take the neighbor direction, make an opposite of that direction, and transform all of the cell IDs accordingly. All right, so let me see now. So this is actually kind of cool. So how are we gonna be doing that? So I think I need a function, which would be called something like opposite dir. Right, opposite dir. Right, so it's gonna switch dir. All right, it's gonna be dir left, right, and this one is gonna be dir right. There we go. So if it is right, this will become left. If it's up, it should become down. If it's down, it should become up. Right, and if it's default, your memory is probably corrupted, so we're gonna actually just do it like this. So it shouldn't be a thing, in my opinion. Alright, so let me see. So what do we have here? Evaluation cell status. Okay, evaluated. Thank you, compiler. Very cool. Alright, so, oh yeah, this is not a thing anymore. Okay. Oh, and this is an absolutely dead code. It shouldn't be a thing as well. And here we have a default. Okay, your memory is probably corrupted somewhere. Yep. So it's going to be something like that. Well, well, it worked, but it's incorrect, right? Because we don't do AST transformation. Like, what? It just worked. It didn't hang, it didn't break, it didn't crash, it just worked. But because we don't do AST transformation yet, it's incorrect. Right, so this is supposed to be 1, 2, 3, 4, 5, and this is supposed to be the left one incremented by 1. Right, so that's actually pretty cool. But the thing we need to do now, we need to translate the AST. Right, so we need a function that accepts expression index, like some sort of a root. And of course, if it accepts expression index, it should also accept expression buffer, EB. And it also should accept the direction in which it will translate the whole AST. So, and the way it's gonna work is that, like, it will traverse the whole AST, right? It traverses the whole AST and replaces cell indices with cell indices moved in that specific direction. That's actually very cool. I really like that. So, let's put it this way. Translate expr in dir, or maybe move in that direction, and this entire thing will return entire index. But we're not going to be modifying, right? Because we just need to actually clone the whole tree. So we're going to be traversing the tree and we're going to be cloning it. And the cool thing is that we can move. We can allocate the new nodes within that buffer right away. Right, as we move this thing in a particular direction, we actually, you know, allocate them in that specific buffer. All right, that's pretty cool. And yeah, a neighbor in dir. And we're gonna use neighbor in dir for all of the translations. Okay, so that's actually really nice. I really like that. Okay, so we need to take the actual expression in here. So this is going to be expression buffer at. So we have expression buffer at, and we provide EB, and we provide the root, roto. So we're going to switch expression kind. And what kind of expressions do we have? Expression kind. We have numbers, cells, and plus. Sus. Plus is sus. I'm not gonna lie. So this is gonna be case. Okay. So this is the number, and of course the default is essentially unreachable. Breach the unbreachable, reach the unreachable, row fight the power. And in here I suppose we can just, if it's if it's a number, we can simply return the number. I think the number does not really require any translation. Cell, on the other hand, does require translation, so I guess we'll have to do something about that. So let me see. Well, I need to have something like new index, right? And the way we allocate things, I think it's an expression buffer alloc. There we go. So here we'll have to allocate a new thing within the buffer. So this is the new index, and in here we're gonna have expression new expression buffer at new index. Right, and in here we're gonna construct a completely new thing. So expression kind is gonna be equal to expression kind cell, right? So this is a cell. Expression as cell, I think. Expression. So expression cell. Yes, so this is S, and then expression. It's a struct expression. I have a huge brain fart right now, I'm sorry. Then as, then plus, and cell is just, cell is already an index. Okay, so here's the cell, and this is where we'll have to translate neighbor in direction, and there we go. So that's the new thing in here. That's a new thing right there. That's a new thing right there. Can you believe that? It sounds fucking believable. Fucking. Alright, so in here we'll have to allocate the new index and new expression as well. But the kind of that expression is going to be expression kind plus, right? So expression kind plus. And as plus, essentially we'll have to recurse left-hand side and right-hand side, I suppose. So this is going to be left-hand side. It's going to be equal to move expression in a particular direction, and we're going to use the left-hand side. We're going to use the left-hand side and that direction, and here we're going to have a right-hand side. There we go. And in here, yeah, I forgot to return the new index. There we go. Return the new index, and here we can also return the new index. So essentially we cloned the whole tree, right, and we moved it in a particular direction. Is it going to compile now? It does not compile because I have to provide the cell itself. Right, and we have a couple of warnings. Unused. Oh, this is because, okay, thank you. Okay, so that's why I always enable warnings for unused variables, because they're quite often a bug. They are in fact quite often a bug. Alright, so we have a function that translates the whole AST and clones the whole AST in a particular direction. So how are we going to be using that? If this is an expression, I need to actually take a different value in here. I actually need to take a different value. So here is an expression, so this is an expression index, and I need to move expression, this specific expression, to a direction that is opposite to the neighbor's direction, right? So yeah, neighbor in direction, so that means I need to take the opposite one in here. So where is my okay, so this one is going to be something like that, and the direction here is cell as clone, right, and opposite direction like this. So this is the opposite direction. I think that's it. So I basically create, like, translate the whole thing, and then I evaluate the whole thing, and then I mark it as evaluated. So if I try to run this entire shit, your memory is corrupted somewhere. The fuck? That's a nice one. Okay, that's cool. So I wouldn't expect that, right? Because you have left, right, up and down. So we hit the unreachable. We reached the unreachable, and we reached it somewhere actually here. My memory is corrupted, yes. My memory is corrupted, though it kind of worked well. You see, this is supposed to be 3 actually. This is kind of supposed to be 3, but I don't know what happened in here. Right, let's make a small break, and after the break we're gonna try to debug the whole situation. Just a second. MM2PL actually said a pretty good thing. We need to check with the memory sanitization of our nation, because I disabled memory sanitization at some point and I just didn't realize that. I'm doing something very sus. Okay, so yeah, memory sanitization didn't really help much. So even though it rebuilt everything, so it does build it with clang and sanitize memory, so I'm probably doing something incorrect, right? So opposite dir, if I take a look at the opposite dir in here, so this is a clone, everything type checks. So move expression in direction, and in here, so root number should stay as usual, cell should be moved in that specific direction, and plus, for the plus we just have to recurse. This is the left hand side and right hand side. So the reason we can try to maybe, it would be nice to know what's the value of that thing. Let's actually see. So opposite direction. So before printing, we can actually print the value in here, just to see what it is. Maybe it will give us some hint on what the hell is going. It's actually 5. Huh. And there is like there's only 4 of them. So why did it become 5? It's beyond me. I don't know. Anyway, so again, I wanted to make a small break and make a cup of tea, so let's actually go back to the break. All right, I got my tea, and let's continue. Just let me sip it real quick. So, so first is a root, and another one is a direction. So there's no problem specifically in here. So cell clone. So cell as clone. So this is a neighbor direction, and it has to be the opposite one. So. There didn't see any problems. Okay, so let's go ahead and GDB this thing. You're overriding as. Not really sure what you mean. I'm overriding as. And that's precisely what I want. I see what you mean. Okay. Okay, thank you. I see what you mean. Okay. So this is direction. Clone, and this is the direction. Thank you. Thank you so much. I would give you the second VIP, but yeah. There we go. This is a correct result. So the input, by the way, was like this, right? So initially, it all starts with 1. This cell basically increments everything by 1, and this one increments the neighbor ones by 1. So thank you so much. Yeah. So we have this kind of shit now. We can have something more interesting, CSV. Right, we can maybe start with 1 in here, and maybe do something like this is supposed to be A, but this is also supposed to be 0, right? So we actually support 0 if you don't have anything in here. So it's gonna be A, B, and so on and so forth. Maybe it's gonna be just 0, so +1, and this one is equals, right? So, and then I can just copy-paste this thing a couple of times, right? And it will increment everything indefinitely. We can even try to do foo CSV, and, well, I mean, this entire thing has to be prefixed with this thing. There we go, so here is that stuff. Then we can do equal A0 + 1 yet again, and then here we can have up and several times here as well. There we go, so it basically increments in both of the directions. Right, so then maybe I can align everything like that. There we go, so it's a little bit more convenient. So in here we can have this one's not A anymore, it's supposed to be like B, right? So because I want to refer to this one, so it's going to be B, and the row is going to be 0, right? B0, and this one is going to be A1, right? I think so, if I understand correctly. So, and it's basically summed up these two things. And now I can try to extend this thing like that. All right, so it cloned it perfectly, I would say. So in here we could probably actually clone that one, right? And what's gonna be there? It actually sums up 3 and 4 perfectly. Right, you see, and 3 and 4 by themselves are also clone things. And we can also clone this entire stuff, now like that. And I think now we can just populate this entire thing. Right, and we have a table, right, we have a table that actually does something sus. Use of uninitialized value at some point. Okay, that's actually pretty cool. We caught some problems. Yeah. But essentially what's going on in here is just we keep copying a bunch of like ASTs and transforming them and so on and so forth. So this is a creeper, by the way. The face of creeper. Maybe creeper is gonna be something like this. I don't know. I don't play Minecraft, I'm sorry. So yeah. That's very interesting. And what's funny is that all of these cells are a clones of these ones with appropriately shifting everything. So yeah, we're basically cloning ASTs and stuff like that. That's actually super cool. I really like this. I think the original exercise didn't have this feature. I think this feature was not was not part of the original exercise, which actually makes it super fucking cool, I think. Alright, so anyway, so we need to take a look at what the fuck is going on in the initialization and stuff like that. So it's gonna be 64. Oh right, which is, so this is here, so we have something that is not initialized. Oh, I see. But this is just a warning, right? And then, oh, okay, I see. Really? Oh, I see what's going on. Yeah, so every time, yeah, I usually, when I allocate a new thing, when I allocate new things, I also mem set it, but I think this time I forgot to mem set it. Yeah, maybe it would make sense for, like, if you're allocating a new thing, just mem set it for me. Why not? I didn't see any reason to not mem set it. Just like, let's do mem set EB items. Alright, so this one is going to be something like this. It's going to be pointer set to 0, size of expression, just 0 initialize that for me. Like, you allocated a new thing, just straight up 0 initialize it for me. There's no reason for it to not be like that. Okay, so let's go here. So there's no need for that anymore. And parse plus, so there's no need to do that anymore. It's 0 initialized. And in here, yeah, so this is new expressions, and that's basically it. Can we just do that now? Use of uninitialized value. That didn't help apparently. 66. Okay. Okay, 496. 496. 417. Okay. Well, this shouldn't be a problem now. Come on. Because I'm literally just doing that. I'm literally initializing it. Literally initializing it for you. Or is it because it cannot recognize that it's not initialized or something? It could be the case, actually. It could be the case. Okay, let's actually go back. And every time I allocate a new thing, right, I allocate a new thing, I'm going to do memset expr 0 size of expr in here. Alright, so another allocation of our nation, memset expr 0 size of expr. Right, and another allocation. Okay, so this is going to be that, memset new expr 0 size of new expr. Right, another allocation. The same thing, I might as well actually copy paste this entire thing. There we go. So I suppose that's what it wants for me, but I'm not 100% sure. No, that's not what it wants for me. Okay. Apparently it's something else. Apparently it is in fact something else. But maybe it's not that big of a problem. So if I go and enable GCC instead, will it cause any problems? Well, it doesn't cause any problems, right? It's just like the fact that we're using uninitialized memory somewhere could be quite dangerous, right? So because different behavior. But yeah, by itself it just works correctly, right? So you can clearly see. So each value in here is a sum of its neighbors, right? So you can clearly see that 63 plus 29 is 92. So that's basically what we have in here. Something like this. All right, so, but if we enable the Clang memory initialization, maybe we can try to do while grind instead. Maybe while grind is going to give us more information for this kind of stuff. So mini cell, so this is actually full CW, and let's do while grind instead. 3 error, 2 errors. Okay, so we've got some stuff in here. Invalid read of size 8. Address in size of a lock. So it's something about X per buffer. Ooh. Is that because it got... We hit... Oh, I think I know what is going on. X per buffer. I have a feeling that we hit this thing that we never hit before. Something like that. So because now we allocated more than 128 elements, and I'm pretty sure if I pre-allocate like 1,000 of them, the problem will go away. It's something with multiplication in here. That's what it feels like, at least. Right, okay, so we're recompiling this entire stuff, and if I try to run it, and it is perfect. Okay, so as you can see, all right, so even if I enable Clang now with, yeah, it is fine now. So there's something with this thing that it doesn't like. So there's something specifically in here, but the question is, what the hell? Oh, are you freaking serious? Like, it wants me to initialize that rest of the... And the fact that I do memset there... Are you freaking serious? Like, every time I allocate a thing, I then memset that thing, but neither Valgrind nor the Sanitizer of Clang are capable to actually detect that. Are you freaking serious? This is embarrassing. Okay, so what can we do in here? I can try to do something like memset EB items, right? So what we're setting in here, I'm going to be setting in plus EB count, right? And the I'm going to set it to 0. And this is going to be size of XPER multiplied by EB capacity, right? So this is going to be capacity minus EB count, I suppose, right? I think that's a good way to do that. Maybe like -1 somewhere. Like it feels like off by 1 somewhere. Right. So we have 0, 1, 2, 3, 4, 5. Right. You had 3, right? So we have 3 elements. So this is count 3, and capacity in here is 7. Right, if you do 7 minus 3, you get 4, and this is precisely the amount of elements you want to initialize. Okay, so that's fine. So there's no off by 1 anywhere here. So now, right, let me try to reproduce that one more time. Right, I'm reproducing that one more time. We're gonna do, let's do sanitization of our nation. Yeah, here it is. And now, if I do that, with a semicolon, of course, it doesn't go away. It really doesn't go away. Use of an initial. This is like a mystery, really. Maybe I don't understand how Realloc works. But there should be no problem anywhere there. This is a real mystery. Is that because the memory gets reallocated and that confuses the sanitizer? Right, because again, if I allocate like a huge chunk of the memory, it is not a problem, right? Because nothing gets reallocated. But maybe because the thing gets reallocated, it confuses the memory sanitizer or something like that. Val grind realloc. Strings give a realloc to make buffer grow when. Okay. I compiled the program, tried it and worked but when I run it with valgrind, the function returns null when the min buffer. When you realloc the buffer, your pointer still points at the old buffer, stomp memory, and also well, I mean that's precisely what we're doing here. That's actually precisely what we're doing. I don't know what could be the problem in here, but again, if we don't do any sanitization stuff, right? If we just don't do any sanitization stuff, it's just not a problem. Like it's just like it's non-existent problem. I don't know. This is a mystery, and I'm gonna leave it up to you and up to people who's watching on YouTube. So if you know what's up with this kind of thing, let me know in the comments, or maybe just send me a message or something like that. Because I don't know. This entire thing seems fine to me, but again, I'm not really good at C programming, so who knows. The only thing I would personally do, right, I would just mem set this item. I think it was a good idea. So I think it was in fact a good idea. So this is going to be size of expression, right, and everywhere where we like allocating this entire thing, we don't need to do mem set anymore, in my opinion. Alright, so, and if I try to rerun this entire thing, there we go, everything seems to be working. How much time does it take to actually, you know, perform all of that? It's actually pretty fast. Look at the performance of this program, actually. It clones and allocates a lot of different things, and it's still super fast, because it doesn't really call malloc very often, right, because it pre-allocates, like, enough stuff. It's actually pretty fast for that program. So we can, well, I mean, there's not that much stuff. Okay, so can we extend the size of this thing? Right. So if I try to run this stuff. Okay. So I'm pretty sure if we're gonna keep stacking this thing on top of each other, it's gonna overflow the double at some point, right? And in here we can also increase this entire stuff. So let's see if it can overflow the double. All right. Honestly, I think for the program that makes this amount of you know, AST transformations and dependency tracking, this is actually super fast. Look, it's just like I'm stress testing this entire thing, and it's just like still very fast. I really like that. Yeah. It's running at 2 PhDs per second. Yeah. This is because we are using like a reasonable way of managing memory for abstract syntax tree, right? So we have a custom allocator for this kind of stuff, and I think on a garbage collected language, this would be a nightmare, I think. But yeah, that's 2 PhDs per second. God damn. This meme is gonna haunt the person who said it for the rest of their lives. I swear to God. My God. All right, so let's do a committee, and maybe then even a push. So we can have some examples, like this is copy, maybe this is gonna be, I can call it stress copy, stress copy, right? So CSV, we're gonna put these things here, so this is gonna be that, this is gonna be that, and this is gonna be that. So this is going to be sum, and in readme input CSV sum. Oh God, that's what I want to have in here. So maybe it also makes sense to document this stuff. Man, I really don't know what the fuck with the memory sanitization. And the fact that we have like such a huge buffer, right? So, and everything is fine is actually just shows that maybe everything is in fact fine. So it's just like, I don't know, it stresses me out. Oh, by the way, we haven't checked the cycle, right? So let's do cycle cycle CSV, right? And this is the simplest cycle that you can have, right? So will that detect the cycle? So this is going to be cycle CSV, and it didn't. That's very interesting. Oh, because I'm an idiot. You're supposed to put it like this. This is the simple cycle. Circular dependency detected. Look at that. Straight up. Circular dependency. We can try to do something like this, and this will actually assert because you're trying to reach the cell that is not available. So we have a boundary check in here, right? So it basically underflew and then it hit assertion, so everything's fine. Though if I put something like 4 in here, 3 in here, it will essentially be just all 3s, right? Because it got cloned or something. Or at any point I can put A, and this is basically A, right? So, and on top of that, it could be also an expression, right? And everything's working exactly as you would expect it. That's perfect. So that's cool. I also never tested like copying from below. Right, so what if it's going to be 5? It also copies from below. So we can put 6 in here just to see. Yeah, so it definitely copied it from below. And if I put up in here, it copied it from above. Okay, so you can just, yeah, everything seems to be working correctly. And I'm pretty sure this was not part of the original exercise. That was definitely not a part of the original exercise. That's a very confused face, not gonna lie. Okay. So what do we have in here? Introduce cell index cell. So, and what we did in here is okay. Implement proper AST translation for cell cloning. It would be nice to also document the cell cloning, right? So we have a quick start, and we can just basically have a section for the syntax, right? So something like syntax. We can have types of cells. All right, types of cells. And how do you do a table in the markdown? GitHub flavored markdown. Aguduk, what's up? You're back. I hope you're fine. Is everything okay? Is everything fine? Table extension. That's how we do that. Sending hooks to Aguduk. Alright. So what we're gonna have in here? So this one is gonna be the name and the description. 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 There we go. So text. Right. Text. Type. Okay. Examples. Examples would be A, B, C, etc. There we go. Then number, right? So it could be could be something like 1, 2, 1, 2. Maybe I think you can also do it like this, right? So because we're using str2d, so text, number, expression, right? Expression, and examples is going to be like this: a1 plus b1. I think 69 plus 420, etc. There we go. And also maybe something like a1 plus 69, and also something like this. Okay. Clone. Man. And it's gonna be actually up. Right. So these are the types of the cells. Maybe we're also gonna have some sort of an you know, description, some sort of documentation, if you know what I'm talking about. So can I move the column somewhere? Mark down column, insert HR. Okay, mark down insert column. Oh, I can do that. Okay, so can I do it somewhere here? Perfect. All right. Can your Vim do that, by the way? Can your Vim do that? I don't think so, actually. Description, text, just a human readable text, right? So anything that can be parsed as a double by str2d, right? Str2d. I'm gonna wait a second. Right. Oh, come on. Everything is so slow. There we go. Oh my god, it's broken. So you know what? I'm gonna move str2d to like here, like this. By the way, str2d, right? And not everybody knows that, but you can actually move some of the links like here, and you can refer to this link like this, right? So yeah, pretty convenient. Starts with colon. Always starts with equal. Excel style math expression that involves numbers and other cells. Toggle truncate lines. Yeah, there we go, fine. I should have toggled truncate lines a long time ago. Okay. Doesn't wrap them around, that's why it's not particularly convenient. So those numbers and all the other cells, okay. So clone. clones a cell, clones a neighbor cell, clones a neighbor cell in a particular direction, denoted by okay, always starts with this thing, clones a neighbor cell in a particular direction denoted by characters left, right, up and down. There we go. Cool. Display lines. So here is the table. So types of cell. Syntax. There we go. So all right. I think we did it. Of course, we have like delete trailing white spaces. Document syntax. All right, we push that. Did I miss? No, I didn't. Oh, I missed it. Okay, thank you so much. All right. Type. All right. So let me see. Okay. Oh, I mean, I'll have to make a pull request, of course. Let's make a pull request. Implement cell cloning, and we're gonna close the seventh issue. And something is not working on GCC. I wonder why. Oh, because it doesn't exist anymore. Okay, so yeah, I moved things around. Right. So, oh, I need to actually go in here. No build.c. Right. So I'm running input CSV. So and yeah. So now it has to be CSV sum. Right. And I can even try to just run this entire thing myself, and everything seems to be fine. All right. Fix the build and push that right into the repo. All right, so we're waiting for the continuous integration. That's actually a pretty cool feature. If the original exercise didn't contain this particular feature, I think it should include it because it's super fun to implement. Right, because you'll have to clone the AST and also translate all of the cell references accordingly and stuff like that. And that was super fun. I really enjoyed doing it. Though I still don't understand what the fuck is wrong with the sanitization. Right. So we can try to report an issue for that just in case, you know, somebody figures it out. Let me see. So I can rebuild everything, right? And then we can do val grind, no build, not no build, but mini cell, CSV. And I suppose, do we want to do stress copy? We can try to do copy. I think it needs to be stress copy specifically, right? Because that will cause. Okay, so yeah, so that's basically what we have in here. All right, so invalid reads in val grind on CSV stress copy CSV. Oh, come on. My keyboard just died in the middle of me typing. What the fuck? Nice one. Nice keyboard, by the way. Okay, so everything's fine. Steps to reproduce. I think my keyboard is like literally dying or something. Alright, so this one is gonna be just no build, and then I can put it like this. Val grind mini cell CSV stress copy CSV. Observed. Val grind reporting invalid reads from only invalid reads, right? And also block allocated invalid reads address inside a block of size. I think I fucking know what the fuck is going on. This shit gets invalidated by this. Holy fucking shit. Prepare, but truly, because you allocate it, so, but you still keep an absolute, okay, holy freaking shit. Oh my god. What the fuck? Alright, so it's kind of funny how, like, yeah, this forced me to, like, go through this entire thing. That's actually pretty cool. How can we... do we really need export anywhere after we checked its kind? I mean, I can just do something like this, I'm pretty sure. So I do need an export yet again, okay. Alright. So... okay. All right. So, if I try to do the memory sanitization for this thing, will it be fine? All right. So this is actually a very interesting way of shooting yourself into your leg. Not gonna lie. Mini cell CSV stress copy, and it still happened. I'm using it actually still, so that's the problem here. I'm still using it, so yeah. Okay, so I need to go through all of the places where we do all that. Okay, so this is fine. So I'm allocating that shouldn't cause any problems. I'm allocating that shouldn't cause any problems. Still doesn't really solve anything. Alright, so if I redirect, I need to rebuild the entire thing. So this time it is use of an initialized value. Maybe with the val grind. Okay, so it's going to be GCC. No build. Val grind. Stress copy. Wait, what? Well, that reduced the amount of errors, at least, right? So that definitely reduced the amount of errors. Right, so this is the only thing I did. So if I put it like this, The amount of errors, well, it's still the same amount of errors. It just literally didn't fix anything. Okay, so let's try to take a look at what's going on here. Move expression in direction. 15. You know what's interesting? This thing can be invalidated by this thing as well. Yikes. Alright, so do you have... Okay, so even though this is a very interesting method, right, even though it's a very interesting method, it's actually pretty error porn, not gonna lie. So let me see. Alright. I wonder if we can... I suppose every time we dereference this thing, we have to do it like this. Like, there is no other way. Right, so we just have to do it like this. Though, interestingly... I wonder if borrow checker would have prevented that. Probably. I think borrow checker would have prevented that. Alright, so... is this not undefined behavior? It is undefined behavior, so this is actually kind of nasty. So... because, like, you have this thing that modifies CB, and you have this thing that modifies CB. Okay, but maybe that's fine. We can try to just run this stuff with Valgrind, right? So this is GCC, and I can try to run it, and 3 errors. That didn't fix anything yet again. Alright, so one more time. Nope, didn't fix anything. Okay, so we can try to do the following thing. So let's actually get rid of the undefined behavior. Expression, right? So, and then the second time we're gonna have this thing like this. Right. I'm not 100% sure if it's undefined behavior and undefined behavior. Okay, so... holy shit, okay. Nope. Nope. That didn't fix shit. What about no build.c? So about the clang. Well, I mean, sure. Cell CSV stress copying. Though now, the sanitizer doesn't really mind this kind of stuff. The sanitizer is fine. Right. So let me switch to Clang. And also no build. Stress copy. Okay. Switch to Clang and run stress copy this way by default. Alright, so this is gonna be that, and if I try to just do no build run, it's fine. And if I stash this entire thing, it crashes. At least on the level of Clang Sanitizer, we fixed that problem. Okay, so I guess this is something, I guess we learned something, right? Even though it's not always like rainbows and unicorns and stuff like that. So with this kind of way of allocating things, it's super easy to shoot yourself into the leg, right? If you're not being careful, right? So because some of the things can be invalidated every time you are reallocating things. And again, if we completely get rid of that and we're only using like this thing, right? So is it still gonna be working with this stuff? Right, if we're doing it like this. Yeah, it is fine. And but what's up with the vol grind? That's the cool question. What's up with the vol grind? I don't really know. Could new expert be invalidated by the allocation? New expert. Shit. You're right. Ta-di-da, ta-da-di, ta-da-da. Okay, so that is very freaking interesting. And that means it's going to be EB new index. All right, so it is working, it is twerking, and if I do something like no build.c and I switch back to GCC, all right, so if I run this entire thing, everything's fine. And now I can do vol grind mini cell CSV stress copy, and 2 errors though from 2 contexts. So maybe this could be something else actually. So we can actually do a similar thing. Well, I mean, this one shouldn't really affect this stuff. Right, shouldn't really affect, I think. But it kind of does. Still. Okay. So let's take a look at the place where exactly it's happening. Maybe it's happening in a completely different place. Table eval cell. Right, table eval cell. 569. Table expression. 5. So, but does it say invalid right of size 8? Block was locked at move expression. So it's all within the move expression stuff. It's all within all of that. Okay, so I guess I'm gonna leave it as it is right now. So let me finish. Well, it reads from expression buffer. Expected no vol grind errors. Though it's kind of strange that Clang FSanitizer does not complain, right? It's only val grind. But again, I don't know. So if I try to run this entire thing, yeah, it's totally fine. So, but I don't know who's more powerful. Probably Valgrind. I think Valgrind must be more powerful than you know, Clank sanitization. All right. So introduce. Let's actually put something like introduced in implement cell cloning. Right. So that's basically what we have in here. All right. Implement cell cloning, and I probably need to commit 7. Try to fix as many Valgrind errors as possible. There we go. I read the repo. I wish there was a language where these kind of like memory allocation techniques were a little bit easier to implement. You know what I'm talking about? Because we're struggling not because this is a bad idea, actually. So this is relatively good idea to like, you know, store things like that. We're struggling because C is a shitty language. I wish there was a language where this kind of like way of manipulating memory was a little bit more convenient and less error prone. I wonder if we have such language or not. Maybe in Rust it would be a little bit safe because yeah, it would be definitely a little bit safe because you won't like the borrow checker wouldn't actually prevent that, and ironically borrow checker would prevent that. So I suppose C++ wrapper with operator override would be too bad in this case. I don't know, C++ is basically as bad as C in this particular case. It doesn't really solve anything in my opinion. So the borrow checker would actually probably kind of help. So what do we have in here? Unsupported for target X. Really? That's very interesting. Sanitize memory. Okay, so I'm gonna fix that. Oh, and we also like ignore the CC variable, unfortunately. Okay. Try to fix macOS build. So C++ is just the avoiding point. Yeah, I don't know, maybe. But I think like Rust's borrow checker, unironically, in this particular situation would actually be beneficial. So I do think so, actually. Like, I'm not even joking. I think it would be beneficial because this is literally like a lifetime sort of problem. And yeah. All right. So did I push everything? JF Vaz subscribed with Twitch Prime for 3 months, by the way. Thank you so much, and welcome to Epic Rust Club. This is Rust, by the way. Is it even building anything? Okay, everything seems to be built. And let's just merge that. So, all right. That was very interesting. I think we learned a thing or two. So why did it say there's 2 of them when there's clearly 1? Okay. I guess that's it for today. Thanks everyone who's watching right now. I really appreciate it. I hope today's stream was interesting. Right. So we implemented interesting memory management techniques and we implemented a very interesting feature. And thank you for all of the subscriptions and all of the support. I really appreciate it very much. You truly make my dream come true. Just sit all day and shit post on the internet, and I really appreciate that. Thank you so much, everyone. And let's maybe, I don't know, rate somebody. So do you guys have any suggestions on who to rate? Is anyone doing anything epic on the science and technology section of platform called Twitch? So let's actually see. Supinic just went live. Okay, so let's raise Supinic, sure, I don't mind. We haven't read it in for quite some time, so all right. So let's wait until this thing will show anything. All right, we're ready for the raid, boys and girls. Get ready for the raid, and I see you all next time. Love you.